Dear students, this is a revision video on phenols. In module 1, you have to learn about the preparation of phenols from halobenzenes, cumene and sulfonic acid, then about the chemical properties like the acidity of phenol, effects of substituents on acidity, then comparison of its acidity with alcohols, then the various reactions of phenols like bromination, nitration, sulfonation, Riemer-Tiemann reaction, Cope's reaction, Lieberman's nitroso reaction, and Lederer-Manesse reaction, and finally the distinction between alcohols and phenols. So this is a structure of a phenol. A phenol is having a benzene ring and an OH group is attached to one of the carbon atoms of the benzene ring. Depending upon the number of the OH groups, phenols can be classified as monohydric, dihydric and trihydric. These are the examples for various types of phenols. Then these are the common monohydric phenols. In monohydric phenols, in addition to the OH group, there can be other substituents at the ortho, meta or para positions. And the substituents can be a single one or two substituents. And the two substituents can be either at the ortho positions or at the meta positions. And in certain cases, all the ortho and the para positions are substituted, like the one in the picric acid. Let us revise the hybridizations of the carbon and the oxygen atom in phenol. The oxygen atom is sp3 hybridized. You can see that the oxygen atom has two lone pairs and this bond angle is approximately tetrahedral, and the carbon atoms are all sp2 hybridized because the carbon atom is double bonded. So because of this sp2 hybridization, this region of the carbon bonded to all the other atoms will be planar. So sp2 hybridization will always give a planar, trigonal planar nature, whereas the sp3 hybridization will give a tetrahedral structure. So during the sp2 hybridization, the three sp2 hybridized orbitals of a single carbon atom are equally shared with oxygen and adjacent two carbons, and the remaining unhybridized p orbitals will laterally overlap with all the other adjacent carbon atoms, forming the delocalization. Let us see and understand the delocalization over the aromatic ring. The first structure is a benzene. In the benzene, there are only carbon atoms and hydrogen. So all the unhybridized p orbitals overlap laterally and the electrons delocalize, forming a ring or a cloud of electron above and below the ring plane. And suppose if an OH group is substituted in the place of a hydrogen, like in this structure, you can see an oxygen atom and a hydrogen atom of the OH group. In this case, the non-bonding electrons of the oxygen atom in the phenol are drawn into the benzene ring. So as a result, the lone pair of the oxygen will become a part of the ring, and this increases the electron density in this region. Let us understand the resonance stabilization in phenols. Here, in the first curve represents the potential energy diagram of cyclohexanol. Cyclohexanol is a 6-membered ring with an OH group. So here at the reactant side, this is a cyclohexanone, and at the product side, it is a cyclohexanone anion. So in the second curve, it represents a phenol forming a phenolate anion. So in both the cases, the phenolate anion is more stable than the structure without the resonance delocalization. So the resonance delocalization gives extra stability to the phenolate anion. Let us revise the properties of phenols. Phenols are slightly soluble in water because the OH groups can form hydrogen bonds with water, but the presence of benzene rings makes phenols less soluble than alcohols because the benzene ring is the hydrocarbon part in the molecule. Then phenols are weakly acidic, that is, when mixed with water, they can ionize, giving off the H plus ions. The H plus ions will be surrounded by the water molecules, and the phenoxide anion will also be surrounded by the water molecules. So this is weakly acidic. And the weakly acidic nature of phenols means that these are neutralized by alkalis like sodium hydroxide. So sodium hydroxide is a strong alkali, so this will neutralize the phenol, forming sodium phenoxide and water. But weak bases, weak alkalis like sodium carbonate cannot neutralize phenol because phenol is weakly acidic. Why phenol is only weakly acidic? Here in this orbital diagram, you can see that there is a negative charge on the oxygen atom, and there are two lone pair of electrons on the oxygen atom. One of the lone pair of electrons will overlap with the ring. The ring is having a rich electron density. So this will overlap with the ring, forming a delocalized ring like this. But still, the oxygen atom is more electronegative when compared to the carbon atoms of the benzene ring. Therefore, there will be a slight shift of this electron density towards the oxygen's region. Even though there is delocalization, there will be a slight extra electron density at the region of the oxygen. So the negative charge now delocalized over the whole ring to some extent. This will shift slightly towards the oxygen. As a result, the H plus ions in the medium will again be attracted back to the O minus anion. So that is why even though the phenol is acidic, releasing the H plus ions, this H plus will have a tendency to come back to this negative region. So the acidic strength of a compound like phenols depends on two major factors. First is the ease of loss of the protons, and second is the stability of the conjugate base formed. So these are the two effects, the inductive effects and resonance effects mentioned here. Now let us see the resonance structures of the phenoxide ion. In the first structure, you can see a phenol, there is a benzene ring and the oxygen bonded to a hydrogen. So there are two lone pair of electrons at the oxygen atom. So when the H plus is lost, one of the electron of the hydrogen is going back with the oxygen. That is why this oxygen is acquiring a negative charge. So as a total, there will be 3 lone pairs. So this extra electron is coming from the hydrogen, and hydrogen is leaving as H plus. So this is the phenoxide anion oxygen is having the negative charge. And in the second structure, you can see the oxygen is double bonded to the carbon. So this negative charge will be given to the carbon atom of the benzene ring, to which the OH is attached. As a result, this double bond will be shifted, giving more electron density to the ortho position. So there are two ortho positions. So two resonance structures are possible. These are the two resonance structures in which the ortho positions will have more electron density. And now the next shift will be that the negative charge is shifting to the next carbon atom. So here a double bond will be formed, and this double bond will break off, giving extra electron density to the para position. So this is the resultant structure. So in all these three last structures, you can see that the resonance delocalization is not there. So it is not aromatic actually. So in these three structures, the electron density is more concentrated on the carbon atoms, whereas in the phenoxide anion, the electron density is at the oxygen atom. So the reason for the acidity of phenol is the extra stability of the phenoxide anion, and that is the resonance effect. These are the resonance effect. It can be represented as plus R or plus M effect. And because of this resonance effect, the OH bond will become weak, and the removal of the hydrogen as H plus ions will become more easy. That is why the phenol is acidic. So if you are asked to draw the resonance structures of phenoxide, now it is easy for you to draw these structures. And in this, the first structure, there is an oxygen atom with a negative charge, and this is a benzene ring with 3 double bonds in the benzene ring. And in the other 3 structures, there are only 2 double bonds in the benzene ring, and the double bond is repeatedly being shifted. And among these 3 structures, the 2 structure is having negative charge at the ortho positions, and one of the structure is having negative charge at the para position. So from this structure, you can understand that the ortho position and the para positions will be more electron rich. Now let us understand the physical properties of phenol. Phenols have OH groups, and because of that they can form hydrogen bondings with other molecules. So this results in a higher melting point and boiling point in phenols, can form hydrogen bondings with other molecules as well as with themselves. So we have compared 2 molecules, phenols and toluene. Even though the molecular weight of these 2 compounds are not much different, the boiling point have a very high difference. In phenol, the boiling point is 182 degrees Celsius, whereas in toluene it is only 111. So you can see here, this is a phenol. 3 phenols are represented here, and these phenols are forming hydrogen bondings with each other. So there is an oxygen atom of the phenol and hydrogen atom of the adjacent phenol. So there is extensive hydrogen bonding in the phenol. Whereas in toluene, there is no electronegative atom and there is no oxygen. So there is no chance of forming hydrogen bonding in toluene. So this results in a lower boiling point in toluene when compared to phenol. Now the next point we discussed was that phenols tend to form stronger hydrogen bonds than alcohols and are more soluble in water compared to alcohols. So the reason for this is that the hydrogens in the phenol is more electropositive because of this resonance stabilization of the phenoxide ion. So when this hydrogen is more electropositive, all the other molecules can form stronger hydrogen bondings with this hydrogen. So as a result, the hydrogen bondings in the whole phenol will be highly strong when compared to alcohols. Then we have to learn about a point, that is the dipole moment of the molecules. Here I have shown a phenol and a methanol, and I have shown the dipole moment of phenol as 1.54 D and the dipole moment of methanol as 1.71 D. So dipole moment is actually a measure of the polarity of the molecule. Polarity is caused due to the charge separation. So here there is a carbon and an oxygen bond. So there is an electronegativity difference here. So there is a charge separation. A separation of charge between the carbon and the oxygen in this bond. Oxygen will be more electronegative, so the electron density will be shifted more towards the oxygen. But due to the resonance stabilization of the phenoxide, even though the oxygen is acquiring a high electron density because of the high electronegativity, it is again pulled back in this direction. So this bond is not that much polar when compared to a CO bond in a methanol. So that is why the CH3OH is having higher dipole moment when compared to phenol. Let us understand the various possibilities of forming hydrogen bondings in phenols. In the first two structures, I have shown an orthonitrophenol and a salicylaldehyde. So here in the ortho position of the phenol, there is an NO2 group. And in this case, intramolecular hydrogen bonding occurs. And in the second case of salicylaldehyde, there is an aldehydic group, that is C double bond OH and an OH group. So in this case also, intramolecular hydrogen bonding is possible between the oxygen atom of the aldehyde and the hydrogen atom of the OH group. Now, there are also different types of hydrogen bondings like homomeric and heteromeric. Homomeric means hydrogen bondings are formed between same kind of molecules. Here I have represented two phenol molecules only. So it is the hydrogen bonding between same kind of molecules. In heteromeric, hydrogen bondings are formed between two different molecules. This is a phenol molecule and this is any alcohol molecule. So this occurs when we mix a phenol with an alcohol or water, any other polar solvents. So this type of hydrogen bonding is called heteromeric. Again, in orthonitrophenols, we previously discussed that intramolecular hydrogen bondings are possible. Whereas in paranitrophenols, intermolecular hydrogen bondings are possible. That is between two different molecules. So this is an example for homomeric hydrogen bonding only. That is, hydrogen bonding is between same type of molecules. Phenols are stronger acids than aliphatic alcohols. And the reason is, of course, the resonance effect in phenol, which makes the phenoxide ion more stable. As a result, the H plus are easily released when compared to the H plus present in the aliphatic alcohols. And we have seen the dissociation constant values of phenol and common alcohols in this range. And phenol is more acidic than alcohols, aliphatic alcohols, because the conjugate base is resonance stabilized. Then comparing the acidity of carboxylic acid and phenols. So here we discussed that carboxylic acid is stronger acid than phenols. In both the cases, there are resonance stabilized conjugate bases formed when the H plus is lost. In the carboxylate anion as well as in the phenoxide ion, there are resonance stabilization. But in the phenoxide anion, the resonance structures, few of the resonance structures have a charge separation. But here, in the case of carboxylate ion, there is no charge separation. Let us see this. These are the contributing structures of carboxylate anion. Okay, this is a CH3 group here. Then a C double bond O minus. The H plus in this OH group is lost. So therefore O minus is formed. So this O minus can shift here and this oxygen can acquire the negative charge in the resonance structure. This is the resulting structure. So whether it is the first oxygen or the second oxygen which is having the negative charge, here the delocalization is very smooth. So these two structures will contribute equally. Whereas in the case of phenoxide, we can see these different structures, and in the first two structure the negative charge is on the oxygen, whereas in these three structures there is a negative charge at the carbon at the ortho and the para positions. At the same time there is also electron density at the oxygen. So this oxygen and this carbon is different in the electronegativities. So this delocalization is not so perfect, or these are minor contributors to the resonance effect. So these two structures, the first two structures are major resonance contributors, whereas the quality of contributions by these three structures are not so good. So that is why in the case of a carboxylic acid, because of this resonance stabilization is very effective, it can easily give off the H plus ions, whereas in phenols this resonance stabilization is not much effective. So here the point is that the quality beats the quantity. Even though there is more quantity of resonance structures in the case of phenol, here the quality of the resonance structures in the carboxylate ion is greater. That is why the carboxylate ion is strongly acidic when compared to phenol. Let us discuss the electronic effects. So electronic effects in phenol is a positive mesomeric effect represented as plus M or plus R, and we have seen the different mesomeric structures of the phenol here. So the electron density on benzene ring is increased, particularly at the ortho and para positions. So when there is a phenol substitution in the benzene ring, the electron density will be more at the ortho and para position. So phenols are ortho para directing. Then we discussed the effect of substituents on the acidity of phenols, and in the case of electron releasing groups like CH3 or OCH3, it is not much important, but in the case of electron withdrawing groups like NO2, Cl or OH, it increases the acidity of the phenol. And if there are multiple electron withdrawing substituents, it will again increase the phenol's acidity. So we compared these three structures in the class. So first was a phenol, and in the second structure there was a Cl group at the para position of the phenol, and in the third structure there was an NO2 group. So in the NO2 group there can be resonance stabilization. That is, extra two structures are possible because of the two oxygen attracting the electrons through the nitrogen. So here this this NO2 group is more electron withdrawing when compared to a chlorine. Therefore, the acidity of the NO2 substituted phenol will be greater. Hence, the pKa value of this 4-nitrophenol is comparatively less. And we can see that the acidity strength is increasing in the order. This is the most acidic, then comes the 4-chlorophenol, then comes the phenol with no substituents here. Then we compared the acidity order of orthonitrophenol, metanitrophenol and paranitrophenol. And the most acidic is the paranitrophenol among the three. Then comes the orthonitrophenol and the least is the metanitrophenol. Okay, because here in this case there is a possibility for intramolecular hydrogen bonding. Therefore, the H plus is not so free. That is why the orthonitrophenol is less acidic when compared to a paranitrophenol. So these are the cases of mononitrophenols. Then we discussed about multi-subnitrophenols, that is phenols with more than one NO2 group. So this is a 2,4-dinitrophenol and this is a structure of 2,4,6-trinitrophenol. So if the number of electron withdrawing substituents in the ring is increasing, this will increase the acidity of the phenol because more electrons are withdrawn from the OH bond in this direction towards the ring. So these three NO2 groups are withdrawing the electron density from this OH bond. So this is the acidity order. The highest acidic is 2,4,6-trinitrophenol, then comes the 2,4-dinitrophenol and the least is the monosubstituted nitrophenols. So the reason is that the higher number of electron withdrawing substituents in the ring will withdraw the electron density of the OH group more strongly, and this will make the release of H plus ions more faster. So these are the electron resonating structures of paranitrophenols and the metanitrophenols. Here there is a question like why this metanitrophenol is least acidic than paranitrophenol, because in paranitrophenol already the para position is having electron rich site because of this OH group, the directing effect of the OH group. Therefore, when an electron withdrawing substituent comes, this withdrawal of electron density will be more effective. Whereas in the meta position, it is relatively electron rich deficient initially, because the OH group is only ortho and para directing and it is not meta directing. So even if an NO2 group comes, this electron withdrawing effect will not be that much efficient. So we can draw only these fewer resonating structures for metanitrophenols. Then the preparation of phenols. We have discussed the preparation of phenols from halobenzenes, cumene, sulfonic acid, then diazonium salts. So in the synthesis of phenols from chlorobenzene, this is an important process called the Dow process. Here chlorobenzene is hydrolyzed in presence of a strong base at high temperatures and pressure of 300 atmosphere to give a phenoxide salt, and this is acidified to phenol. This is the Dow's process. So you can prepare phenol from chlorobenzene. So this is a method for conversion of benzene to phenol. Here benzene can be first converted to chlorobenzene using Cl2 and FeCl3 catalyst, and from the Dawes process we can convert this chlorobenzene to phenol. In the second method, phenols can be prepared from cumene. So for that, initially benzene is converted to isopropyl benzene. Benzene is treated with propylene, and at the double bond this benzene and hydrogen is substituted, and we get this is an addition reaction, and we get a cumene here. This is the structure of cumene. We have a benzene ring and a CH having 3 CH3 groups. And this cumene, when oxidized, we get cumene hydroperoxide, that is COOH bond is formed here. And this cumene hydroperoxide is hydrolyzed and we get a phenol. So this bond breaks and the OH group is substituted at this carbon. So we get a phenol and an acetone is formed. So this part will form the acetone. So in this case we get two valuable industrial products, that is the phenol and the acetone. Then we discussed about the preparation of phenol from benzene sulfonic acid. Here also first benzene is treated with sulfuric acid in presence of SO3. This mixture is called oleum, that is sulfur trioxide dissolved in sulfuric acid, and this will substitute an SO3H group at the one of the positions, any positions of the benzene ring, and this is called benzene sulfonic acid. And when this benzene sulfonic acid is treated with sodium hydroxide followed by the hydrolysis, acid hydrolysis, we get an OH group in place of the SO3H. Then we discussed about the preparation of phenols from diazonium salts. For this, benzene is first reduced to aniline, and this aniline is treated with nitrous acid, that is NaNO2 and HCl, a mixture of sodium nitrate and HCl at very low temperature, and this will give the diazonium salts. Here nitrogen, there are two nitrogen molecules here, so the N will acquire a positive charge here. So this is a diazonium salt, and it is highly reactive in nature, and upon warming with water we get a phenol. So this nitrogen is released, then HCl is eliminated, and the resulting product is a phenol. And this is a very important reaction, and this diazonium intermediate can be used for the preparation of many other organic compounds. So the chemical reactions of phenols. So the reactions of phenols discussed in your text, it is categorized as 3: reactions of the phenolic group, reactions of benzene ring, and then some special reactions. So let us see the reactions of phenolic group. First is the formation of salt. So this phenol, when reacted with a base, this is acidic. So this is an acid reacting with a base to give salt and water. The salt is the sodium phenoxide. And again, in the place of NaOH, you can take sodium OH. So this is a very vigorous reaction in the presence of sodium metal. This reaction will also give you sodium phenoxide with the release of hydrogen. Then the action of zinc dust is shown in your text. That is, a phenol when treated with zinc dust, benzene is formed. So this is a reduction reaction. The OH group is removed from the phenol, and zinc is a catalyst, and when it is heated, a zinc oxide is formed, and the OH group is absent here. You get a benzene from this reduction. Then you have the action of ammonia. Here also phenol is reduced actually. So this NH2 group is substituted. For this, anhydrous zinc chloride catalyst is used, and phenol when treated with ammonia in the presence of anhydrous zinc chloride, you will get aniline. Then you have the reactions like acid chlorides and acid anhydrides. That's the acylation reaction. Acylation, this is the acyl group, CH3CO group. This is the acyl group, and this compound is acyl chloride. So when a phenol is treated with acyl chloride, the acyl group is substituted at this position, at the high position of hydrogen. So we get phenyl acetate. And another important reaction is Fry's rearrangement, and this we didn't discuss in the class, but we can cover it now in this video. So here in Fry's rearrangement, a phenyl ester is treated with aluminum chloride in aqueous HCl, aqueous acid, and the resultant product are either ortho or para substituted aryl ketones. So here an ester is converted to a ketone. So this is a kind of rearrangement reaction. So previously we discussed a reaction. These were reductions, and this is a acylation reaction, and this is a kind of rearrangement reaction. So intramolecular reaction involving the migration of an acyl group from phenolic oxygen to ortho or para positions of the ring. This is a Fry's rearrangement. Then Shorten-Bowman reaction of phenol is also important. This is a benzylation reaction, that is the phenol when reacted with a benzoyl chloride. Benzoyl group is C6H5CO. This is a benzoyl group. There is a carbonyl functional group here. So when this phenol is treated with benzoyl chloride, in place of this hydrogen, C6H5CO group will be substituted. So this is phenyl benzoate. This is the Shorten-Bowman reaction of phenol, and the other product is HCl. Then there are reactions of phenols with phosphorus halides shown in your text. That is phosphorus halides. Two phosphorus halides are present in your text, that is PCl3 and PCl5. Both show different reaction. In the case of PCl5, when phenol is treated with PCl5, only the OH group is substituted and one chlorine replaces. So this is a chlorobenzene. And then the other products are POCl3 and HCl. Whereas in the case of PCl3, there is another compound formed. Here chlorobenzene is not formed. In that place we get a C6H5 thrice PO3. Here 3 benzene rings are present in this compound. So the reactions of the reaction with trihalides, that is PCl3, PBr, etc., does not give haloarenes, that is chlorobenzene or bromobenzene, but it gives a phosphorus ester. This is the compound. Then you have the reaction of phenol with neutral ferric chloride. Here also this is a test for phenol. When this phenol is treated with the neutral ferric chloride, you get a violet compound which is shown here. This is a neutral ferric chloride, and when you pour this some phenol into this compound, you get this color. So this color is due to the formation of this particular complex. Okay. Then the reactions of benzene ring in phenols. In the class we discussed the bromination, nitration and sulfonation reactions, and additionally we can cover alkylation, acylation, mercuration and nitrosation. So these are all electrophilic aromatic substitution reactions, that is substitution occurs at the aromatic ring of the phenol. So in the electrophilic substitution, this is an electrophile E+, and E+ will be attracted to the electron rich sites of the phenol, and we get the ortho and para isomer. So phenols are highly activated towards electrophilic aromatic substitutions, and the OH groups in the phenol are ortho-para directors. And in the nitration reaction, in bromination and sulfonation, these are the different products formed as a result. In the first case, the HNO3, when phenol is treated with dilute nitric acid, NO2, single NO2 group is substituted either at the ortho and para position. In the bromination with CCl4 as a solvent, also similar substitution occurs at the ortho and para. Single bromine atoms are substituted, and when the concentration of this bromine is increased along with a slight increase in temperature, 3 positions the substitution occurs. And again with concentrated sulfuric acid, only at the ortho position SO3, ortho as well as para position also the SO3H will be substituted. So this is the bromination reaction. Phenol, when it is brominated at low temperature, we get ortho and para-bromophenols. Whereas when it is when concentration of bromine is increased, bromination of phenol with an aqueous solution, that is in treatment with bromine water, we get 2,4,6 tribromophenol. So let us understand how this bromine addition is occurring. A bromine molecule, a slight polarization of the Br bond occurs, and the delta positive part will come and attach to the electron rich site of the benzene ring. So this is how the bromine is being attacked by the phenolic group. So here a substitution occurs at the ortho position. As a result, there is a slight shift in the electron density, and this hydrogen is eliminated by the following Br minus ion. So the HBr will be eliminated, and this is the resulting product. So bromination, if deactivating groups like SO3H, NO2 or COH groups are present at ortho or para positions of phenolic ring, they may be replaced by the halogens. This is an additional point. And then we come to the sulfonation. In sulfonation also, the sulfonic group will be at the ortho and para position at low temperatures. So then we studied about nitration. Here at 20% of nitric acid concentration at low temperature, you get 2 nitrophenol and 4 nitrophenols. Whereas at concentrated sulfuric acid and concentrated nitric acid treatment, the phenol will give picric acid. So this is the color of picric acid. This is a yellow color compound, and the yellow color is due to the chromophoric effect of the NO2 group. And in this part you can get questions like what is this picric acid, and what is the structure of picric acid, and why is it a very strong acid. Okay, so we can see why this is a very strong acid. In picric acid there are 3 NO2 groups, and these 3 NO2 groups are withdrawing the electron density from the OH group. As a result, the OH plus ions is easily released. So this is the reason for the high acidity of the picric acid. So this is there is no carboxylic group here, but still it is called acid, picric acid. The reason is that this H plus is very easily ionized in this compound. You can see the pK value is very low, 0.38. So this is a very strong acid. It can even react with very weak bases like sodium carbonate, which gives off the carbon dioxide. So there are different methods for the preparation of picric acid. Commercially, it is prepared first by sulfonating a phenol and then by nitrating the product. So when we sulfonate first at the ortho position and the para positions, the sulfonate group will be attached, and followed by this, when we nitrate it, all the ortho positions and the para positions will be occupied by the nitro group. So we get the picric acid finally. And why are we using this sulfuric acid for the nitration of phenol? This is because this H plus ions of the sulfuric acid, it can protonate the nitric acid. So this is a resultant structure. This oxygen of the nitrogen acid will be attached with the H plus ions, and as a result, this part is a water molecule. This will be easily released and the NO2 group will be free. So the intermediate is a nitronium intermediate, and this nitronium intermediate is having a positive charge at the nitrogen, so it can readily attack at the electron rich center of the phenol. So this is the role of sulfuric acid in the process of nitration. So this is a cut short from your text. Phenols react with concentrated nitric acid in the presence of sulfuric acid to form 2,4,6-trinitrophenol or picric acid. And picric acid can also be prepared from chlorobenzene. Chlorobenzene, when treated with nitric acid and sulfuric acid, nitration occurs, and in this case the ortho and para position NO2 groups are substituted. Then this is subsequently treated with aqueous sodium carbonate, and ultimately this gives this makes the chlorine ions to leave. So in this place the OH group will come. Again, this when treated with nitric acid sulfuric acid mixture, we get a picric acid. So the extra addition is the role of the sodium carbonate. So from chlorobenzene you can get picric acid. First is the nitration, then treatment with this base, and then again nitration. Then from trinitrobenzene also you can get picric acid. So here this compound is trinitrobenzene. So there is only 3 NO2 group, and this is not OH, this is only a hydrogen here. So in the laboratory, picric acid can be prepared by the oxidation of this compound with a potassium ferricyanate. It's a very good oxidizing agent. So this will give the picric acid. So another point is that picric acid, it can be used for the synthesis of picramide. That is, the OH group is substituted by the NH2 group. For that, at first the OH group is treated with a PCl5, and this causes a Cl group to attach here in the place of OH. This is the compound, and this is picryl chloride. And again, this again on treatment with concentrated ammonia, an NH2 group is substituted in place of chlorine, and this is the picramide. Then you have another important reaction, that is Friedel-Crafts reaction. Generally, a Friedel-Crafts reaction are two types: alkylation reaction and acylation reaction. In alkylation reaction, you can see this is a benzene ring only, this is not phenol. This in alkylation reaction, an alkyl group is substituted at the benzene ring, and in acylation an acyl group is substituted at the benzene ring. So the common factor is that all these reactions, it can be done on either a benzene ring or a phenol or any other aromatic compound, but the catalyst used here are the same, that is AlCl3. For an alkylation, an alkyl halide and AlCl3 is used. In acylation, an acyl chloride and an AlCl3 is used. So this is the mechanism here. This is a Lewis base here, that is an alkyl halide, alkyl chloride, and when it is treated with an AlCl3, aluminium chloride acts as a Lewis acid. So here this electron density is shifted to the aluminium. Aluminium is electropositive. so it is a metal. So this excess electron density of the chlorine is shifted to aluminium. This creates a positive charge with the chlorine, and you get a structure like this. This is a complex, and as a result this alkyl part will leave. And here you can see a tertiary carbocation. This is an electrophile. Electrophile is a carbon based electrophile with positive charge on the carbon. And the other moiety is the AlCl4 minus. So here 4 chlorine atoms are there attached to aluminium, and aluminium is having a negative charge here. So because of the generation of this electrophile by this AlCl3, this alkylation reaction can occur very smoothly. So in your text there is an alkylation reaction of phenol, that is in alkylation reaction a CH3Cl is reacting with phenol in anhydrous AlCl3. You get this alkyl part substituted at the ortho or para positions, and you get this orthocresol and paracresol. And in the acylation reaction, the reagent is CH3COCl, acyl chloride. Again the catalyst is the same, and this acyl group is substituted either at the ortho or para position. So this is the Friedrich-Crafts acylation reaction, and the first one was the Friedrich-Crafts alkylation reaction of phenol. Again in mercuration, phenol on refluxing with aqueous mercuric acetate. This is a mercuric acetate. So here there are 2 acetate groups. Mercury is having a +2 charge, so acetate is having a -1 charge. So 2 acetate groups are required in mercuric acetate. So this phenol can undergo mercuration. So the resulting product is orthoacetoxy mercury phenol. This is the structure. And the other molecule of acetate will be converted to the acetic acid. Again in nitrosation also the NO group is the additional substituent. This is not nitration. Nitration, the NO2 group is the substituent. In nitrosation reaction, the phenol reacts with nitrous acid, that is a mixture of sodium nitrate and HCl at a very low temperature. And in this case, in the para position, orthonitrophenol is attached. And after this, this structure will undergo a tautomerization, that is the N double bond O will be converted to NOH. And you can see that this benzene ring is being converted to a only 2 double bonds inside the ring. So this is para-benzoquinone monooxide. This is the monooxide part, and this is the quinone part. So in the quinone actually there are 2 oxygen atoms, but here in this case one of the oxygen atom and NOH group is there. So that is why this is monooxide. So that is in the para position, para-benzoquinone oxide, monooxide. This is the nitrosation reactions of phenol. So again we have to understand about the reactions of dihydric phenols like catechol, resorcinol and quinone. These are also important compounds, and it has many applications like preparation of dyes and all. So first we will learn about the catechol. Catechol is the structure. At the 1,2 positions there are 2 OH groups, and for the preparation of catechol, orthochlorophenol, that is a phenol in which the ortho position chlorine is substituted. This can be treated with sodium hydroxide, a base, at 460 Kelvin and pressure, and this chlorine atom will be substituted by another OH group from the sodium hydroxide. So this is the catechol. So in this compound, the second compound, 2 chlorine atoms are there. This is ortho-dichlorobenzene. Here also, when this compound is treated with sodium hydroxide, the 2 chlorine groups will be substituted by OH group. This is from this method also we can obtain catechol. Another method shown in your text is from glycol, that is OCH3 group is present in addition to the phenolic OH. Here an acid hydrolysis is done, and this group leaves, OCH3 leaves, and instead of this group an OH group is formed. Then again another important reaction is Dakin oxidation reaction. So here in this a salicylaldehyde is treated with alkaline hydrogen peroxide. The salicylaldehyde is treated with hydrogen peroxide and sodium hydroxide and hydrogen peroxide mixture, and two OH groups are substituted. So this HCOONA will leave. There is sodium formate, it will leave, and water is another byproduct. So this is the Dakin oxidation. So catechol is prepared by the oxidation of salicylaldehyde with alkaline hydrogen peroxide. This reaction is called Dakin oxidation. Then we see the uses of catechol. Catechol is used for manufacture of alization dye, that is alizarin. So this process is called alization, and this is a process for manufacturing dye, and it is also used as photographic developer. It is used as an antioxidant, and there are so many uses for catechol. Then another last important one is the synthesis of adrenaline, and this is a hormone drug. You can see the structure of adrenaline here. In the structure of adrenaline you have this catechol part, and followed by there's another structure like this. Okay, CHOH, CH2, NH, CH3. This is the structure of adrenaline. Then let us see this preparation of alizarin from catechol and phthalic anhydride. This is only one of the technique for preparing this alizarin. So catechol is treated with phthalic anhydride. So phthalic anhydride is derived from phthalic acid only. This on heating, one water molecule is lost and phthalic anhydride is obtained, and this compound reacts with this catechol, and we get alizarin dye. This is the structure of alizarin dye. This is 1,2-dihydroxyanthraquinone. Next we discuss about a resorcinol. In a resorcinol, it can be prepared from 1,3-benzene disulfonic acid. It is treated with the base. We get ONA group attached here, and again which on treating with acid we get OH group here. So these are also the synthetic methods for the preparation of a resorcinol. And again here you can see a stephinic acid. Stephinic acid, it is obtained by the treatment of 1,3-dihydroxybenzene with nitric acid and sulfuric acid. So here NO2 groups are substituted at 1, 2, 4, 6 positions. So this is the structure of stephinic acid. Then quinol. Quinol is 1,4-dihydroxybenzene. For the preparation of quinol, it is prepared by the sulfonation reaction of para-benzoquinone. So here initially aniline is oxidized to para-benzoquinone. So it is oxidized. At the para positions you have two oxygen atoms, and this benzene ring is changed to this double bond, the two double bond structure. And the structure when treated with sulfurous acid, it gives a quinol. So sulfurous acid, it will give H+ ions to the oxygen. So the resulting structure is quinol, and this oxygen and this benzene ring delocalization is replaced in the resulting structure. This is the structure of sulfurous acid. So here this quinol again it can be oxidized to para-benzoquinol when treated with FeCl3 and water. So here this is a reversible reaction actually. So this reaction even quinol in this type of reaction is used for the in electrodes for the determination of H plus ion concentrations. So you can measure a pH of a solution using an electrode having these chemical compounds, and the name of this electrode is quinhydrone electrode. So we see some special reactions of phenol. So these reactions we discussed in the class, but we will go through this once again. And the last one is Gattermann's reaction, and first is the Riemer-Tiemann reaction. So Riemer-Tiemann reaction is a conversion of this phenol to salicylaldehyde. So phenol is reflexed with a chloroform in the presence of an alkali. It can be NaOH or KOH. So the alkali is a strong alkali. And this reflexation is carried out at 340 Kelvin to form orthohydroxybenzaldehyde, or this is the orthohydroxybenzaldehyde or the salicylaldehyde. So if the ortho position is occupied or hindered, then the Riemer-Tiemann reaction substitution of the CHO group will occur at the para positions. So in this case of orthogressol, the ortho position is substituted by a CH3 group. Therefore, the substitution the bonding of the CHO group will occur at the para position. So we get a 4-hydroxy 3-methyl benzaldehyde here. Again, the Riemer-Tiemann reaction can also be carried out in the presence of CCl4, carbon tetrachloride. So in this case, we get a carboxylic acid group, COH group instead of the aldehyde group. That is the difference. Now let us see the mechanism of the Riemer-Tiemann reaction. This is very important. And the first step is the generation of the electrophile. So CHCl3 first it reacts with sodium hydroxide. This is the OH minus over here, and this will abstract the proton, and this is the resulting structure. So there is a negative charge at the carbon. So this structure is not stable, so a chloride anion will leave immediately. So minus Cl minus here. So this will give a CHCl2. Sorry, CCl2. This is CCl2. This is dichlorocarbene. So dichlorocarbene, this is the structure of dichlorocarbene. It is having a vacant orbital, and since it is sp2 hybridized, it is a the lone pair of electron will be present at the sp2 orbital. So this is an unhybridized vacant orbital remaining free. So this is an electron deficient compound, and this will attack the phenol at electron rich sites. So the next step of this reaction is the reaction of this dichlorocarbene with a phenoxide. So here the phenol in the medium will react with sodium hydroxide forming phenoxide, and this phenoxide is having electron density at the ortho position. So the dichlorocarbene will come and attack at the ortho position, forming a bond that you can see here. So in the next step there is the hydrolysis. So there is excess base present in the medium. So as a result of this hydrolysis, what happens is that one of the chlorine atom will be replaced by the OH from the base. So in the next structure you can see that there is a carbon attached to an OH group from this base, and there is a remaining hydrogen and the chlorine. So this hydrogen, it came from the benzene ring only. You can see here the hydrogen in the blue color. So this is a hydrogen ring that was initially attached to the benzene ring. So this hydrogen ring is shifted to the dichlorocarbene's carbon during the reaction, and in the next step this chlorine will leave, and you can see that in the place of this chlorine also another OH group will come and attack. So as a total there are 2 OH groups substituted in this carbon, but this type of OH substitution is not stable. So this will form an aldehyde, C double bond OH. So you can see the mechanism from your text. First is the generation of electrophile, as we have previously discussed. This is a CHCl3 in the presence of a base from sodium hydroxide. A proton is subtracted and water molecule is eliminated. Initially we get CCl3 minus. Since Cl minus is not good at attaching here, it will leave off and a dichlorocarbene electrophile will be formed. This is electron deficient. And the next step, this dichlorocarbene will react with phenoxide. So at which position? The ortho position, phenoxide will, the dichlorocarbene will come and attack. Again there is a shift in the bonding at this site, and this hydrogen in the benzene ring will be shifted to the carbon. So we get a CHCl2 here. This resonance structure is replaced here. So this is the structure orthodichloromethyl phenoxide. So here there is a phenoxide part and there is a dichloromethyl part at the ortho position. And the third step is the hydrolysis. There are excess OH minus in the medium, and this will come and get all the chlorines. There are 2 chlorines here. This will come, OH minus will come and get replace all the chlorines here. So 2 OH bonds will be formed here, but this is not stable. So a water molecule will be eliminated and we get an aldehyde group here, CHO group. So again there are H plus ions in the medium which will come and attach to the phenoxide O minus, and we get a salicylaldehyde. This is the mechanism. And then in the Riemann-Tiemann reaction with CCl4, the products are carboxylic acid, actually 2-hydroxybenzoic acid. This is salicylic acid. So now there are also additional points to be noted in this section. Here the dichlorocarbene is attacking only at the ortho position, not at any other positions. Actually in the phenol the para positions are also electron rich, but dichlorocarbene always come and attack at the ortho positions in the case where all the other positions are absent of substituents. So this is because of the 2 reasons. First is the extra stabilization caused by this cyclic transition state structure. Then another reason is the electronegativity difference between this oxygen atom and this carbon atom in the ring. So oxygen will be more electronegative, therefore it will not easily give off its electrons to the electron deficient dichlorocarbene. Therefore the ortho position of the benzene ring will be having more tendency to give its electron to the dichlorocarbene. That is why the dichlorocarbene is attacking at the ortho position. Then we discuss the Lieberman's nitroso reaction. Here a phenol is reacted with sodium nitrate and concentrated sulfuric acid. So this is the whole process here. So in the first step, a phenol when it is treated with nitrous acid, always we get a nitroso group at the para position. So this nitroso group is always subjected to a tautomerization, and it will be converted to NOH. OH bond will be formed, and this resonance structure will be lost, and this is the resulting structure at the para position. So in the next step, another phenol molecule will come and attack, conjugate at this para positions of the structure. So this is the second step, or a phenol, and the structure is reacting, and we get a complex like this, a conjugated structure like this. This is a blue or green in color. And again, this structure, when it is treated with water, what happens is that the accompanying HSO4 minus ion from the sulfuric acid, this part will be lost, and indophenol, a red or brown color, will be formed in the solution. This is the complex here, which is causing the red or brownish color. And again, if it is treated with sodium hydroxide, this OH group will be replaced by ONA. Again, this color will be transformed to a blue or green. This is the indophenol anion. So this is a Lieberman's nitroso reaction. Then Cope-Smith reaction, it is also very important. Here phenol is treated with sodium hydroxide, and this sodium salicylate generated is treated with the acid. So we get this two Na plus ions are replaced with H plus in this. We get orthohydroxy benzoic acid or salicylic acid. Then Lederer-Manesse reaction, it is also called as Baekeland-Lederer-Manesse reaction or Baekeland reaction. So this is the whole process of preparing the bakelite polymer. This is a phenol formaldehyde resin. For this, first the formaldehyde and phenol is reacted, and in this process the formaldehyde, it is converted to a positively charged species initially. So you can see this CH2 double bond O reacting with a catalyst. Either acid catalyst or a base catalyst can be used. Here I have represented an acid catalyzed reaction. So this H plus will come and attack at the oxygen, and this will create a positive charge in the oxygen initially, and this will cause a resonance shift. Then oxygen atom will lose the positive charge, and instead the carbon will get the positive charge. So this is an electron deficient species. So the electron deficient species will come and attack the ortho position of the phenol, forming a CH2OH bond. Okay, both the ortho position and the para position can be equally attacked. And in the next step, there is a condensation reaction between different ortho substituted and para substituted compounds. So you get a straight chain compounds like this. Here the an ortho substituted phenol is condensed with another phenol molecule. So here the benzene is having a hydrogen, the phenol is having a hydrogen here. This hydrogen will condense with the OH group of the CH2OH, and water will be lost. So this two ring will be connected using a CH2. So this is the compound. It's a straight chain compound. This is a linear polymer. So again, in another step, this type of linear polymers can be networked using para substituted products like this. This is a ortho substituted and a para substituted product, and this can form networks like this. Here also the linkage will be only CH2 linkages. So here like this the whole compound can be networked. So these are the monomeric units, and this is the polymer. So this is a polymerization reaction. Then we discussed about phthalene reaction. In phthalene reaction also, phenol is treated with phthalic anhydride in the presence of concentrated sulfuric acid. The mixture is heated, you can see this phthalic anhydride is having the carbonyl group. So the carbonyl oxygen and the hydrogens from the para positions of the phenol will be lost as water molecule here. So the resulting structure is a phenolphthalein. This is a dye. So this is an important reaction that is phthalene dye test. So in the phthalene dye test, phenol is reacted with phthalic anhydride in presence of sulfuric acid. We get phenolphthalein, which is initially colorless. So this is the compound here. So here this structure, when it is treated with the base sodium hydroxide, the OH groups are removed. Instead of that, you can see an O minus here and a double bonded oxygen, and again this chain is also broken. This anhydride chain is also broken. You can see COO minus here, and this complex is a pink color. Again, if you are treating it with excess of NaOH, the OH group will be substituted at this carbon also. So carbon is tetravalent, so it have to satisfy its 4 valency, either from the benzene ring or from the anhydride part or from additional OH group. So when this compound is treated with NaOH, this compound is formed, that is, which is a colorless compound. So this is the phthalene dye test. Then there is a coupling reaction, that is a coupling reaction between a diazonium salt and a phenol. So coupling occurs at the para position. So we get para hydroxyazobenzene. This is a benzene diazonium chloride and a phenol. Coupling occurs at the para position, and this is the final compound. This is an orange colored azo dye. It is called azo because it is having 2 nitrogen atoms bonded with a double bond. And again, in this case, if the para position is not free, this coupling occurs at the ortho position. This is another reaction, Gattermann's reaction. We didn't discuss it in the class, but we can see it here. So in this, a phenol is reacted with HCN and HCl in presence of catalyst AlCl3. So the final product will be an aldehyde, salicylaldehyde. So in this case, actually, initially an HCl will react with HCN to form a compound like this. So here nitrogen is having a positive charge, and this compound, this positive charge will shift to the carbon when this bond is shifted to nitrogen. So this carbon part will come and attack the phenol ring. So that is why we get a imine. Either at the ortho position the attack can occur, or at the para position. This is the structure of imine. And when this imine is hydrolyzed, the ammonia molecule is lost, and in this place what a CHO functional group is formed. So Gattermann's reaction, when phenol is heated with a mixture of hydrogen cyanide and hydrochloric acid in the presence of aluminium chloride or zinc chloride. Either aluminium chloride or zinc chloride catalyst can be used. So an aldehyde group is introduced in the ortho position of OH group in phenol. That is, a salicylaldehyde is formed. So Gattermann's reaction is a reaction for the preparation of salicylaldehyde from phenol. And the reagents are HCl and HCN in the presence of AlCl3 catalyst or zinc chloride catalyst. There are also some miscellaneous reactions given in your text. First is the oxidation reaction using chromyl chloride. Para-benzoquinone can be formed from phenol. Other oxidizing agents like potassium persulfate can also be used for oxidizing quinol. but this is less oxidizing, that is a paraquinol is only formed. And in the other case, chromyl chloride is much more stronger, so we get a para-benzoquinol, that is two oxygen atoms are double bonded to the ring. Then the most important oxidizing agent is always the KMnO4. It is very strong. So in the case of KMnO4, you can see that the phenolic group, this is a paracresol. So phenolic group is the CH3 part is oxidized to a carboxylic acid group. This is KMnO4 is a very strong oxidizing agent. So in order to treat this type of compounds with KMnO4, you can see that there are two functional groups here. This is a CH3 and a OH. So KMnO4 is very strong, therefore it has a tendency to oxidize this OH group also. So in order to prevent this, we have to protect this using another group like CH3CO group from the acetyl chloride. So this is a protecting part, a protecting reaction. So here the oxygen atom, this OH group is protected using CH3CO group. After that only KMnO4 is used for oxidizing the CH3. So in this case only the CH3 part will be converted to the COOH part, and after the oxidization of the CH3 part, we can again replace this OH group by acid hydrolysis. Acid hydrolysis will cleave this bond, and OH is replaced here, and the acetyl group will be leaving. Then you have the hydrogenation reaction. This is actually the catalytic hydrogenation of phenols. So here, if you are using a nickel catalyst and hydrogen gas, we can remove this unsaturation in the benzene ring of the phenol. So you get a cyclohexanol as the resulting product. This is the catalytic hydrogenation reaction. And in another reaction, you have ammonolysis. Ammonolysis means some breakage or some cleavage. Here the OH bond is cleaved here, and in that place the NH2 group is attaching. So the phenol, when it is treated with ammonia, in the presence of zinc chloride catalyst, it gives aniline. So this is an ammonolysis reaction. Then in the last part, we studied about the important difference between alcohols and phenols. Some general points. In the alcohols, OH groups is attached to the alkyl group. Then whereas in phenols, it is attached to the aryl group. Then you can see that hydroxyl derivatives of alkenes are called alcohols, whereas phenols are hydroxyl derivatives of benzene. And the compounds in which one hydrogen atom of water is replaced by an alkyl group. So this is an alcohol. So here phenols are compounds in which one hydrogen atom of water is replaced by aryl group. So actually in this point, these compounds can be considered as a derivative of water. So in water we know that there is an oxygen atom attached to two hydrogen atoms. So in water molecule, if one hydrogen atom is replaced by any other group, we can simply say that that compound is a derivative of water. So that is what this point is saying. Then the general formula, alcohol ROH, and the general formula of phenol is C6H5OH. Then in lower alcohols, these are colorless liquids, whereas phenols colorless crystalline deliquescent solids. And alcohols have a characteristic sweet smell and burning taste, and phenols, whereas they have characteristic phenolic odor. And you can see the pK value comparison here. Then alcohols are readily soluble in water, but the solubility decreases in higher alcohols. Why? Because the hydrocarbon part is increasing in higher alcohols, so therefore the solubility of higher alcohols decreases in polar medium. Whereas phenols are sparingly soluble in water, forming a pink solution but completely soluble above 68.5 degrees. So this is a CST experimentation and all. So then in alcohols it will react with two ways, that is reaction of the CO bond, reactions in which the CO bond breaks, and then the reaction in which OH bond breaks. So in phenols only you have the resonance structures, but in alcohols it do not have the resonance structures. Then again there is another type of comparison shown here now with 5 points. So in alcohol do not have any effect on litmus paper because they are neutral. So litmus paper, blue litmus is turned red only by acids. So phenol is acidic because because it is acidic, it can change blue litmus to red, but alcohols won't do that reaction. Then the alcohols have no action with the bromine water, whereas phenols it will give a white precipitate because bromine is substituted at the benzene rings at the ortho and para positions. So, and the third point is if alcohols develop no characteristic color with neutral ferric chloride solution, but we saw that this phenol it can form complexes with the Fe3 plus ions in the FeCl3 solution. So because of that complex, these phenols can give color to the medium. Then fourth point is that alcohols they cannot show any coupling reaction with the arene diazonium salt, whereas phenols will show coupling reactions. So azo dyes can be obtained from phenols after converting it to the diazonium salts. And the last point is alcohols do not react with the sodium hydroxide, whereas phenols do react with sodium hydroxide to form phenoxide ion. So that's all for the revision. Thank you.